trailer.
What do you think, Doctor? What do you think, Daniel Sama?
Okay. Oh, I'm looking at our wind energy. There it is.
Here, Dan. How good do you think this game looks after seeing this trailer? Damn it. No. There it is.
Sure, it's not the beginning of Star Wars.
Nope.
Yeah, that's the beginning of Star Wars. It's the beginning of every Star Wars.
Is it?
It's the beginning of Diablo 2.
What you watching now?
Halo 5 trailer.
What?
Halo 5 trailer.
Alright.
Oh, it's totally Diablo 2.
Does it sound off?
No, it's on. It's kind of quiet, but.
Oh.
Yeah, see this. I mean, the end boss is a little larger.
So that did that? Oh, that did. Okay, yeah, I remember trying to remember what that was. Yeah. Fucking weird.
It's the front door to his house.
Bing bong.
Why would he ring his own doorbell?
I feel like the wife and kids know something.
Oh, I guess that makes sense.
Honey, I know. How good does the game look from just after this?
Wow. That's a cinematic trailer, dude.
Yeah.
Oh yeah, but that's supposed to represent the game that's coming out. It's the official trailer for the game.
It's got hooks.
It's got hooks.
It's like, hey, what's this thing? Why is it in the desert? Was it hiding there? Who's in it?
Exactly.
Whose is it?
Oh,
Can I drive it? Are the keys in the ignition?
there wasn't even a desert mission, was there?
No,
Yeah.
it wasn't. It was the biggest lie you have ever seen in a minute and a half.
Yeah, and that thing is only in like a minute of the game.
For real. Until at the ending.
Yeah. Like, you play 60 hours for that.
That's so true. Well, it's totally
Anyone have any philosophical questions they want me to write on the board?
Why is Halo 5 so trash?
That's not a
Philosophical?
question.
Can I ask you a dumb question?
Do it.
Cool. So, I am entertained by stupid shit. Right?
As
Welcome
as
to the
most
club.
people are.
So I can literally be entertained by just a cup of water. Got it?
Okay.
So, when I dip my finger, let's just say that's my finger, into the cup of water, right? For some
wet
reason,
finger.
yeah. So the surface tension of the water does
Okay,
that,
that's
right?
me. Well, okay, sorry, keep going.
So that's what I see
Uh-huh.
when I look
Your
at
eyeball?
Yeah.
Okay.
Whatever. So how come when I go underneath the water, right, and I look at it from there, it goes like that?
Wait, what?
Like what?
When you look underneath,
Yeah, when I'm underneath the water and I look at it,
so you're under the water poking
Yeah.
at yourself.
I'm just like doing this, and I'm underneath it.
I don't think I've ever
It
done that.
touches.
I've never done that.
It touches the water
You see your
like that,
finger
but
on the
above, the water's surface tension does that.
Drop yourself.
Wait.
I'm trying to kill myself so I can't answer this question.
Just distraction showing you.
Yeah, that's what I was gonna say. It's just diffraction, but
That's what I've been told, but you know what's always a follow-up question for the professors?
what?
I really don't know.
Yeah, well,
That's always the follow-up question. I'm like, come on, you're like my physics teacher. I'm
give me
like,
some water. Give me a bowl of water.
Yeah.
That's empty.
We also need multiple observers.
You need to do 50 trials.
All right, I'm gonna go.
we need a month's worth of data.
I'll
And
be right
compute
back.
the uncertainty within your finger.
Dude, we need a month's worth of data every 10 minutes.
You know, a 24-ounce cup of coffee would get through this one.
Oh, you'll be fine.
I need you to put a mask on.
Oh yeah, my bad. I forgot.
I need you to see my thumb drive.
This single thing was pointing at you. I'm like, what did you do?
Oh.
Yeah, see my thumb drive. It's right here.
Today is Friday, right?
Where's that? Wait, last time said 410, right?
4:15.
Oh, okay.
4:15. I got water. Where'd Jason?
He was so sad that you didn't immediately answer.
Well, I got water so we can test
Are you
it.
serious?
Yes.
Oh. You just went to go get water because you need
Okay, we need one person under looking up and one person above verifying.
Dude, I see the same thing.
Yeah, I don't know what he's talking about. I just see my finger in the water.
Yeah, no, it's refracting towards you, so I'm seeing that it's going in.
Guys, if you're gonna do that, take 5 steps this way so the camera can see it.
Oh.
It's only, I have no idea what you guys are. So,
Yeah.
it looks like it's going down. It does look like it's going up.
Yeah, it looks like it's going
Y'all should ask Derek if you could.
That's a
replace
great
that with
question.
I think he drew it backwards.
I think he drew it backwards.
I think he drew it this way. So
Wait,
that's
yeah.
what he sees looking down
Mhm.
and looking up
You
when you're
see.
down here.
Oh, we're still talking about this?
I got water to
If you own a home in Washington,
We think you drew it backwards.
Well, yeah, but my point still stands.
let me
Yeah,
show you
yeah,
a little
Pretty
secret
sure
on
on
like
top
I
it
didn't know
looks
about.
like this.
Well, either way, my
And
point still
then
stands.
under.
Dude, how'd you even come to this conclusion?
He just did what we just did.
Like, where'd
he
you
wants
get
to know
this
why.
idea from?
Wants to know
the first
why?
place?
Yeah, right? You wanna know
Oh,
why,
so,
right?
Are you asking like initially, how
Yeah.
did I come across this question?
Yeah.
I was chilling in a hot tub, and then I was thinking, yeah, no, because I go in like, yeah, I was deep in thought, and it's just like, whoa, really? Like to test zero gravity is literally either underwater or like a fall, or like you're falling.
You're
right?
falling, yeah.
That's it, and I'm like, that's super cool, and I start dipping my finger in the water. I'm like, oh, cool, the water just catches like that. I'm like, does it work like underneath as well? And it looked the exact same, and I'm just like, whoa, why does it do that? And no one's been able to answer my question.
So I think
So you all
this,
think about
this is
water.
this is straight up right out of the water. This is straight up just because of hydrostatic tension.
Yeah.
Right. In the water, I think it's because of the way the light's reflecting through the curve. It reverses
yeah,
the
reflects,
image.
reflects the thing. That's what I've been told. But again, every professor follows it up with.
Seeing this way.
You
I
wanna
don't
give him an
know.
answer, Dr.
Well, we're not.
that?
Wanna give him an answer?
One, I'm not following what the question is. It's not a good time. Two, it sounds like an optics question.
Yeah, and we're none of us are optics.
And I'm not an optics person.
So
I'm an
The
optimistic.
light refracts this way,
absolutely.
right?
Yeah, and so
So-
you'll see the opposite image. So up
No,
here,
give
the
me
light
an answer.
refracts.
Dr.
Back there, so it looks like this.
Professor Venture from UCC could have gave you an answer.
So basically, whatever your eyes. Like here, there's no flex back down.
Good. Yeah. So
Good.
So yeah, just like whatever your eye sees, just there. It just sees the same thing, but underneath the water.
because
There, is that a better eye?
Your eyes are fine.
your idea is fine because it goes boop 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 reflect boop boop boop. So yeah, I noticed it shifted down, but yeah, you just see this point at the same, and then the angle for up here is gonna hit. come out this way. I don't know. I'm not an optics guy, but I think that's what it is.
You're in 306, right?
Yeah.
So you should propose an alternate lab.
I need
Verify-
a month's worth of data.
What,
Every
10
10
minutes.
minutes,
Yes.
I just check.
Yes.
well, no, how would you verify it? You could have an object dipped in water where it's grounding this way,
Mhm.
and then from underneath, have just a
Camera.
visual camera, and then have another object slowly approach and just verify that the light is refracted
Then I gotta
one
test
way
it at
or
a
the
different
other.
angle. I gotta test it at like a 45-degree angle.
Yeah, you see?
Dude, you should find a optics
Because
engineer.
we weren't messing around long enough to really come to any good conclusions.
I just stuck my finger in it.
Yeah,
This is anecdotal evidence.
we were making more jokes than we were honest observations.
I wasn't really expecting an answer. That was just a thought that keeps occurring in my head. That's it.
Yeah, you can't ask us questions like that.
If nobody was gonna feed it.
Well, without us going on a tangent.
Absolutely.
Damn, all I think about non-showering is when I'm gonna eat things.
A lot of this stuff there.
That or nothing, man.
I'm thinking about what I'm doing.
A shower?
That or just vibing to the music that's playing.
That would be interesting.
Oh.
Actually, mostly what's been going through my head is, what am I doing at the gym next?
Mine is,
How can I fix this?
in the past 3 days, it has been, what do I have to do?
Yeah.
Do I have time for this shower? Nope.
5-minute shower.
I'm seriously, if you just have it in the back of your head, ignore it.
Dude, I already got it.
Have fun.
I like this running.
You're not getting started already.
Last time I read a book was like middle school.
Last time I read a book
It
was
takes
like
away
2
from
months
the
ago.
learning value time.
Did you like a book?
No, I have that already.
Yeah.
Did you like the second?
No, I didn't even want the first one.
Would you like an autograph sound?
You, yeah.
At all stages of my writing on it.
That was true.
Just say co-author the stage.
Add one more page.
Move it on and also
This
just come back to
means
it.
absolutely.
Exactly.
Oh, it's 14. Let me.
Go fish with some drag.
Real quick.
Kind of pitching moment. Pitching moment.
Oh, yeah.
Building the turbines should have been easy.
You would think so.
Okay, I have 4:15, let's go ahead and get started. Bremerton, can you hear me all right, and are you watching, seeing content?
Coming up.
I can't.
Yeah, we're good.
I'm coming.
Okay, how about Holman?
Yeah.
Do you see? Great. Okay, I want to stay back up to speed with what we were talking about. We were just starting with aerodynamics, kind of big picture aerodynamics 101 stuff. And I wrote this down for you to remind yourself. So we have a lift coefficient, a drag coefficient, and we have a feedback moment coefficient. So I want to get going back where we were talking about, but I also want to mention, since we're gonna have class today, we'll have class on Wednesday, and on Friday, we have our first kind of like, I'm calling it a mini exam. Okay, it's only about 35, 40 minutes long, tops. I don't remember what I said. I think I said 35 minutes in the syllabus. I don't want to dedicate an entire class to an exam. So I hope we cover some material after the exam. I'm a little worried that we have been in COVID world for the last year and a half, and that people, and I know a lot of the students don't come to this lecture live, they either watch it at home, in real time on Zoom, or they watch it recorded. This exam is not gonna be online, it'll be on paper. You can't take it from, it's not like questions are magically gonna show up on Canvas, right? The assumption is that you are in the classroom, that you are assigned to be in the classroom during the exam. If you are not in the classroom during the exam, and it's only a 35-minute exam, if you show up late, that'll really eat into your exam time. All right, so there will be a proctor in Pullman, and I'm talking to somebody. I haven't gotten confirmation yet, but I'm sure I'll find somebody in Bremerton who will proctor the exam. All right, so it is a proctored exam. I haven't written it yet, although I have a pretty good idea what it's going to look like. But I'm not going to tell you what that might be because I might change my mind. But it will be about 35 minutes long. It's going to cover basically chapter 1 and chapter 2. And I haven't given you any homework on this yet. And I don't know what kind of homework I give you on this, but there may be some general questions. You should know and be familiar with the derivation of the Betz limit. Okay? At very least, you should know what the Betz limit is, both numerically and what it represents. Okay? You may be asked some general question about the derivation, but I'm not expecting you to have memorized the derivation, nor am I expecting you to be able to carry out the derivation on your own in 35 minutes. Okay?
Clarification question. So you said
Yeah.
that we don't have the content that's on the exam will not have been on our homework. Is that correct?
I'm sorry, can you repeat the question?
The content on our test, will that have been on our homework previously? Like, will we have seen it before, or will it be different material?
Yeah, okay. So what I'm saying is I haven't given you a homework on chapter 3 yet. So the exam is going to cover almost exclusively the general stuff from, the general overview stuff from chapter 1 and chapter 2.
Okay, gotcha. Thank you.
And however, there may be we discussed the Betz limit and we discussed the modified Betz limit last week. I haven't given you homework on that. I reserve the right to ask you a general question that will involve you understanding what the Betz limit is and maybe understanding some general big picture aspects of the proof of the Betz limit. Okay. But the most important, the one thing I really want you to get out of me talking about the exam day is you have to be in a classroom to take it. Okay. So that's what I wanted to say about that.
Really quick.
Question. Will we get an equation sheet or do we have to memorize the equations beforehand?
I will give you a certain number of pages of notes that you're allowed to write. Probably 1. It might be 2. I'll probably do the same thing I did in statistics, which you guys don't know because you're seniors, that's a junior level 5. I'll give you 2 front pages. Okay, so I'll ask you to turn in your notes with your exam. And because of that, and because they'll be scanned from Pullman and Bremerton, I'm going to ask you to don't write on the backs, and so you have 2 front pages. But I'll after class today on Canvas, I will write this all out, and it'll be under module for week 6, and I'll write up on like okay what's allowed, what's not allowed on the exam. Are allowed, by the way. Yeah.
One more tiny thing, is gonna be like parts of it is multiple choice and parts of it are regular problems.
That's the stuff that I don't want to say right now. I have in my mind what's it going to be like, but I am going to write it over the weekend.
Okay.
I'm not.
No, it's okay.
Yeah, all I can tell you is what I'm thinking, and then if I change my mind, then you'll be upset. So, and rightfully so. So, But ask me again on Wednesday and I might be more forthcoming on that.
Okay.
Alright. Okay, so, let me just real quick, get us back up to, we were talking about some different terminology that you need to know about airfoils. Alright, so you should know what a leading edge is, you should know what a trailing edge is, you should know what the chord length, what the chord line is and what the chord length is. You should know the difference between a chord line and a camber line. And you should definitely know what I'm talking about when I say angle of attack. Okay. And when I say you should know, not for the exam. You should know this going forward. Okay, this stuff won't be on the exam. All right. But you should know it for exam number 2, for example. All right. So again, because this is an airfoil, and because we built the airfoil for a reason, and that reason is because it has some force acting on it. When it's exposed to wind, it creates a resultant force. We as human beings break that resultant force, and we decide that any part of that resultant force that's in the direction of the flow, we call that drag. And any part of that resultant force that is normal to drag, we call lift. Whether or not it is actually lifting the airfoil or not. There's another load that we have to consider. There's also the tendency that the airfoil is going to want to turn, okay, or rotate. That is because of the pitching moment. And we measure the pitching moment as acting from a point 1/4 length along the chord line, and we call that the quarter chord. And then what we ended with yesterday, or Wednesday, was that it has been discovered that for the most part, that the ratio of your lift and this is your dynamic pressure, 1/2 rho the velocity squared, that ratio is more or less a constant for a given angle of attack. For a given angle of attack and given Reynolds number, but practically not even for a Reynolds number. More or less, it's just dependent on your angle of attack. Okay, so which is convenient because when we can catalog this lift coefficient, or this drag coefficient, or this moment coefficient, and then for any similar airfoil of any size at some given angle of attack, we can say, aha, that is what the lift force will be. Okay, so it's usually written like this, but in reality, what you're going to do is you want to know the lift. And so you look up what is my lift coefficient at that angle, at the angle of attack, at some angle of attack that you're interested in, times 1/2 rho the velocity squared and the area of your the area of your wing or your blade or your airfoil. Okay, and that'll be your lift. Okay, and that's usually what you want to know is, okay, I want to know my lift, and I can look up my coefficient, my lift coefficient. All right, so there's an obvious question to ask, which there is an answer to, but some really, really, really smart people don't all agree on the answer. Okay, and that is why. Why do airfoils create lift? And there's a lot of competing explanations, and I'm going to give you the standard explanation that's in our textbook. It's almost every undergraduate textbook on why airfoils create lift. Okay, so I have an airfoil. And I'm going to draw my airfoil more or less symmetric. And I have air that upstream from my airfoil is smooth, consistent, uniform air, which you call U infinity. So the air is going to have to intersect, when it intersects with the airfoil, what's going to happen is the air on top has further to travel, and it has further to travel, and it is going to speed up. So the air on top is going to be greater than U infinity. That's supposed to be top. So there's this guy, pretty big, important guy, named Bernoulli. And Bernoulli said, Bernoulli says that my pressure plus 1/2 rho u squared is a constant. I mean, he threw a z term in there too, but we're not changing the heights here, okay? So we have a Bernoulli equation. So if my velocity on top is higher, that means my pressure is lower. Okay, and what bugs a lot of people is what is often said, not in our textbook, but in some textbooks. It'll say something like a particle of air that goes over the top has to get to the end of the airfoil at the same time as a particle of air that goes on the bottom. So you have your leading edge, and any piece of air that's just on this type of leading edge is going to go over the top, and any piece of air that's just on the bottom of the leading edge is going to move along the bottom. And the argument is they have to get here at the same time. And because this guy has a longer path to take, he has to move faster. And that's what a lot of textbooks say. Okay? And that is kind of right. Because if he's not moving faster, if they don't get here at the same time, and there's a whole bunch of those particles, that means there's less air on the top than there is on the bottom. And if there's less air on top than there is on the bottom, that means there's a partial vacuum on top. If there's a partial vacuum on top, then the airplane's going to want to go up, which it does. Okay, so so that you could use that to explain lift. All right, that this guy has, and if you do a CFD simulation that accurately models the real fundamental first principles, you'll actually find that a particle of air that starts out here and a particle of air that starts here, they don't actually reach the vacuum exactly at the same time. But still, this guy on top is moving faster than the one on the bottom. And this Bernoulli equation is accurate and it is true. The air on top is moving faster than the air on bottom, and there is a pressure difference on what's on top and what's on bottom. Now you'll hear other really smart people say, no, it's not Bernoulli. It's Newton's third law. The air on the bottom, when it hits the airfoil, has to go down. It goes this way, and so it starts moving down, and then inertia is going to keep it moving down. That is true. You have an air particle, it hits this, it's going to bounce this way. And if it bounces this way, it's going down, it's going to keep going down until there's some force that acts on it that goes in another direction. Okay, that's also true. So if you go on YouTube and you type in why do airplanes fly, or why do airfoils cause lift, you'll see people from MIT arguing with people from Harvard about this. And to me, it's like, look, Bernoulli equation is based on conservation of energy. It's a fundamental law of the universe. It cannot be wrong. Okay? I mean, it doesn't always apply, but it's a best case scenario. You can't get worse than this. I mean, it's accurate. And Newton's third law is also a fundamental principle. The thing is, they both have to be right, and they're both right. The argument over which one causes which is it amazes me that really smart people spend a lot of time arguing that one is smarter than the other, when in reality it's like, you're both stupid because you wasted that much time talking about it.
I have a question.
There's a third argument. I'm sorry, was there a question?
Yeah. Have you heard about the book trying to prove that 1 + 1 = 2 using set theory? I think it's 2 parts.
I don't know about set theory. Oh wait, 1 + 1 = 2? 1 + 1 doesn't,
Yeah.
is that what it is?
That's what the whole book is on. It's trying to mathematically
Oh,
complete.
no, actually, yeah. So there's a really funny, like, I'm really into watching British TV, and there's a really funny, like British panel show where they talk about that. And the thing is, it's not that he wrote this book on like why 1 and 1. What he actually did was he basically put all of math on firm footing. He put all of mathematics. He proved basically that mathematics is right? That it's all consistent, which nobody had done before. But it all begins with proving that 1 and 1 is equal to 2. And apparently somebody mentioned that the guy also had really bad that. And it was like really funny. It's like this guy, he like, first off, what a guy to be at a party. Like, oh, so what do you do? Oh, I proved that 1 is equal to 2. And on the other hand, you did this like amazing mathematical feat, and the one thing that people remember is, oh yeah, he had a really bad breath. All right, so there's another argument, which is also completely valid, which is that the air around the airfoil, because of the shape of the airfoil, on a net way is rotating. It causes circulation. So you can also explain lift in airfoils by, which I'll do a little bit more mathematically rigorously in a moment, show that it's actually because the air begins to rotate around the airfoil, and this also creates lift. Okay? And I'll explain that in a little bit more detail in a moment. So one of the important things that you have to think about is that there's, you have to understand that there are inviscid inertial forces and there's also friction. And so when you're looking at airfoils, let me draw another airfoil. I'm going to draw this bigger. There's two regions that we're interested in. So we look at inviscid flow. And we look at inviscid flow away from the airfoil. And in inviscid flow, we assume there's no friction. So we basically assume that like the Reynolds number is like really, really high, and we can ignore friction. And then we have to look at the boundary layer, where friction dominates. And if you're trying to find the lift, if your interest is in finding my lift, I can almost perfectly explain the lift on the airfoil and determine the lift just with inviscid flow theory. And inviscid flow theory is nice because it doesn't have friction, and friction makes things complicated. But really close, like millimeters or sometimes centimeters away from the blade, and it gets thicker the further you move along the blade, is a boundary layer. And in boundary layer, friction dominates. And if I want to understand stall, I need to understand the boundary layer. So, and let me just say, so in viscid flow theory, I'll say for first order, approx of that. So what we do a lot of times is we just ignore the boundary layer. For the sake of understanding what is the lift on the airfoil. And then when we want to know where the airfoil is going to stall, then we need to start thinking about the boundary layer. So let me attempt to explain this. I think I can do this on this page. So as I mentioned the other day, I showed you some plots on a website. And I'm going to just show you one corner of this plot. So this is, my x-axis is angle of attack, or alpha, that was supposed to be an alpha. And this is my lift coefficient on the y-axis. And what almost all of these plots look like, regardless of the airfoil, is you have more or less a straight line with some slope. And at some point, it reaches a maximum and then very quickly starts to decrease. At this point, this is referred to as stall. And while I'm here, we're not gonna use this today, but we'll use this later. Sometimes you'll see the slope of this line, of this more or less line. Sometimes you see this written as alpha CL. Okay? It's the slope of, it's a slope, and it's more or less constant for small angle of attack of your alpha versus CL line. Okay? All right. So what causes this stall? And I guess I was wrong. I couldn't fit all on the page. I wrote that too big. All right. So let's zoom in on an airfoil. So this is the edge of my airfoil. And this airfoil, the way I've drawn it, we're going to say that, remember that is the top of the airfoil, so our velocity is increasing. In this direction. And if my velocity is increasing, that means my pressure is decreasing. All right, so my pressure is increasing, my pressure is decreasing, my velocity is increasing. So if I look at the boundary layer, that means this is my mean flow. And here, my velocity is getting faster. So, no problem. I'm in good shape. Now, I'm going to draw another airfoil. And because we usually see this effect when you have a larger angle attack, I'm going to purposely make this a little bit steeper. And if the airfoil has a fairly large angle of attack, or I don't have a very good shape to my airfoil, and again, I'm along the top, and now I have, again, this is my mean flow velocity, but now, for some reason, my far stream, my away from the airfoil velocity is decreasing. As I go in this direction, which means pressure is increasing. So if my pressure this way is decreasing, this means that I have a negative pressure gradient. but here I have a positive pressure gradient. So the pressure is higher here than it is here, inside the boundary layer. So what's going to happen is I have a relatively large, thick, my velocity profile is nice and large. And then as I get here, this velocity is smaller, and I've got pressure. Pressure is higher here. So the pressure starts wanting to push the fluid this way. Because the fluid wants to go from an area of high pressure to low pressure, right? So if the pressure is higher here, now the pressure is going to start slowing it down. And eventually what's going to happen is, even though out here, away from the wing, I still have positive velocity, at the wing, so I'm going to get something that first is going to look like that. And then eventually, my boundary layer is going to look like this, where the fluid next to the wing is now reversed. And what that's going to happen is, now I'm going to get turbulence, and I'm going to get what's called detachment. And so the air is no longer attached to the wing, and it becomes highly turbulent. So one thing about this, when detachment occurs, so this is flow is detached and I say stall. However, this does not mean the entire wing has stalled. The airplane's not going to crash right now. It's not usually the way it happens. What usually happens is I have some angle of attack and I get a little bit of, so I'm still getting positive lift here. But this is no longer creating lift. And then if I got a little bit steeper, and I'm way exaggerating that, like this would definitely stall if it was like this angle attack, then the detachment might happen here. And so what happens is, as you increase your angle of attack, the area of detachment moves up closer and closer to the top of the wing. And at some point, you don't have enough low pressure area to create lift. Another thing I should have said, because I remember when I was an undergrad, and quite frankly for the first year of my grad school, I didn't wrap this around my head. Pressure is force divided by area. Okay, that should be a mantra. Okay, so when I say that I have high pressure below the wing and low pressure above the wing, right? And this is happening because this means that the air beneath it is pushing up on the wing, and there's a lot of it. So there's high pressure and it's pushing up on the bottom, and there's air above it, and that is also pushing on the wing. But it's less pressure. And each one of these arrows, remember, think of each one of these arrows as now acting on a certain area of the wing, which means that there's a force. So there's more force pushing up than pushing down. And that's why airplanes fly. And, oh wait, what was this last? And why wind turbines spin. All right.
I have a question.
Okay. Yeah, go ahead.
So if you're on a plane, for example, or a turbine, does this mean that if it's spinning faster, then you will have less separation? Detachment, flow separation, detachment.
So I'm maybe see if I'm understanding this correct, what you're saying correctly. Let's say it's an airplane,
Yeah.
okay, and the airplane is flying up really fast. You're
Yeah.
suggesting that maybe because the air would push on the boundary layer, then there'd be less separation. I mean, that seems to make logical sense to me, but I don't think the effect would be that big. Because we're talking about the separation starts to occur in this very tiny area that's usually only a couple centimeters away from the wing. And I think that like if you're in a wind turbine that's spinning really fast, or you're in an airplane that's increasing its altitude really fast, I think that might decrease the size of the boundary layer by a little bit. But I don't think it'd be like enough to get you to stop from stalling.
Okay.
But that is a good question, and I'm sorry, I don't actually know. I don't know the answer for sure, like how much of an effect, but I'm sure it's not that big an effect. I want to talk. All right, so somebody asked me at the end of last class, how do you, without knowing the lift coefficient, how do you determine lift for like an airfoil that I don't have the polars, like somebody hasn't done experiments for. I'm going to address that a little bit right now, in that we're going to talk about potential flow theory. And I should say, look, I'm just going to give you the big outline of potential flow theory. I could teach, or somebody could teach, like a 3-week mini course on potential flow theory, and we're not gonna do that. I'm just going to give you the big picture. So potential flow theory this is what I'm saying is like we're looking at inviscid flow. And so I'm ignoring boundary layers. And flow is laminar. And I don't know if I like. Okay, I'm gonna say ignoring boundary layers, but we still have the no slip condition, which contradicts each other. But I need to. We're gonna, for the most part, we're gonna say, all right, there's no boundary layer. Let's say I've got a cylinder. In a cross flow. So I have fluid flowing around this cylinder, right? So it's uniform fluid upstream. And if this cylinder is just sitting there and it's not rotating, so this is a non-rotating cylinder. Then nothing terribly exciting is going to happen. All right, the fluid's just going to flow around it. Just as much fluid is going to flow on top as on bottom. The fluid on top is going to have the same velocity as the fluid on the bottom. And nothing terribly exciting is going to happen. Now, here's what's cool. Let's say I did the experiment again. But this time, my cylinder is rotating. And again, this is a completely different situation. I have uniform flow upstream. What's going to happen, and this is the part where I can't ignore the boundary. I have to at least say there's no slip. So this particle, this point is rotating. So the air that sees this point, it has to stick. Remember, it's no slip condition. So it can't, it has to move at its own velocity plus the velocity of this point. So the air up here is moving faster. And the air down here, this point, which is moving in this direction, and this particle of air it's going to be stuck here, right? Because of no slip. So if this thing is rotating so that at this point and this air, so that it's rotating at such a velocity, its angular velocity just such that its angular velocity times its radius is equal to this velocity, that particle air right here won't even be moving. Well, Bernoulli said that pressure plus 1/2 u infinity or u squared is a constant. So if this air is moving faster than this air, and this is lower pressure than this air, and I will get lift. And our textbook doesn't go into this, but if you're interested, and I would be, this is called the Magnus effect. Because some guy made Magnus. And there are, there's been an attempt to make airplanes that work on this. Really humorous attempts. Although I have seen on YouTube, somebody successfully made a Magnus effect drone using KFC chicken boxes as the rotating cylinder. And there is also, this has been used on some ships instead of sails. They have let's say rotating cylinders instead of sails. And they use this for ship. They're actually talking about using it for cargo shipping. All right, so now we're gonna get into some really heavy math, but not for long. All right, so mathematicians. I need to explain some coordinate system here. All right, so for the cylinders that I was just talking about above, we're going to call this direction x, and the velocity in that direction is u. And the velocity in this direction we're going to call y, and the velocity in that direction we're going to call v. Almost like we're in a fluids class. All right, there is this mathematical fluids concept called vorticity. And vorticity, which they usually use a Greek symbol that I can't draw repeatedly to save my life, so I draw it like that, is equal to the change in the velocity in the x direction as you change the y direction minus the velocity in the y direction as the x direction changes. Okay, and vorticity has when vorticity is it's a measure of how much the flow is moving towards some point. And there's this other concept called circulation. Which is the tendency for the fluid to flow around an area. Okay? The circulation is how much the fluid is making circular, but not necessarily spiraling towards some central point, but how much the fluid is rotating. And it can be shown that circulation, we use the Greek letter capital delta.
Yeah.
Delta. Okay. It can be shown that the circulation is the double integral of the area, so the integral over the area of my vorticity So this is the same as okay, so this is important because if we cause the cylinder to rotate, we can find out what du dy is, and we can figure out what dv dx is for every point in the velocity field. And then we can carry out this integration, and we can figure out what the circulation is. So the big payoff on this is that it can be shown that the lift per unit length, or so L is the lowercase l is just the length of the, so it's the lift per unit length is equal to rho u infinity times my circulation. So rho I know, u infinity I would know, I can figure out my lift of this rotating cylinder. And this rotating cylinder, from this and from the definition of the lift coefficient, I can find out that my maximum lift coefficient is CL equals 4 pi. For this type of Magnus effect. And by the way, the effect is called the Magnus effect. This isn't important for this class, but if you're interested, the effect is called the Magnus effect. But if you actually try to build one of these things and use it, they refer to it as the Flatner rotor. Okay? So if you like, you can Google like Flatner rotor, like sailboats or Flatner rotor airplanes, and you can find some really hilarious YouTube videos of airplanes taking off and then crashing into the ground. Well, because the problem, the thing is, with the early attempts to make one of these, the thing is, 4 times 3.14 is a number larger than 12. And a lift coefficient of 12 is a humongous amount of lift. So if you can actually build one of these things, like you should be able to build an airplane where it doesn't have wings, it just has rotating cylinders where the wings should be, and they'd be much smaller. The problem is if there's this other aspect of Newton's third law, that for every action there's an opposite and equal reaction. So if you've got your wings on your airplane spinning really fast, the entire rest of the airplane wants to rotate in the other direction. Which they didn't quite figure that out in the 1920s when they were attempting to make these airplanes. All right, so why do we care? So if you're a mathematician and you've got some coordinate system, well, I'll call this X and Y, and I've got this rotating cylinder in the middle of it, and I've calculated its lift, I can perform a transformation and go move this to another coordinate system, and I'll call this X prime, no, I'll call this X prime. Why did I put that here too? Where every point in this plane maps to a point in this plane. And however, I come up with this transformation in such a way that the points on this circle map to this point in such a way that my new mapping is some airfoil shape I'm particularly interested in. So this is like, basically I'm saying like, this point right here might map to this point. And this point right here might map to this point. And I can use this to figure out, okay, if I know the lift here, again, assuming I'm ignoring friction, I'm ignoring the boundary layer, but I can do this transformation, I can therefore then know lift here. And it's a complicated mathematical process that was covered in some graduate level course I took, but not to the level where like I was actually expected to do this type of transformation. But there is software code that does this and does this type of transformation and can give a good approximation for a particular airfoil shape what the lift is going to be. And what has been found from this analysis is that, and this is something you need to know for a homework assignment that I'm going to eventually get around to writing. But for a thin airfoil, this result at low angles of attack we can find that in this scenario, our lift coefficient is approximately, for, again, it has to be a thin airfoil and it has to be a low angle of attack, is approximately 2 pi alpha. And this is fairly good for an angle of attack of less than 0.13 radians, which is approximately 7 degrees, I believe. I Googled that right before coming to class. I seem to remember that. That was what I came up with about 7 degrees. So for small increments of attack, our lift is more or less some constant. Well, we know that it's linear, right? I said that it tends to be linear for low angles of attack. And so it's linear essentially with a slope of 2 pi. Okay? This is angle of attack, and this is CL. This would be saying that this slope here would eventually be 2 pi. And again, our textbook doesn't point this out at this point, but if this is only valid for 0.13 radians, so 0.13 times 2 times 3 is about 0.8. So these really thin airfoils up to about 7 degrees, which is a fairly decent sized angle of attack, you're getting a lift coefficient of less than 1. Whereas a rotating cylinder, you could get 12 if you could make it work, which has been the hard part. Oh, the other hard part is, the nice thing about airplane wings is that they don't stop. Right? You don't have to. I don't have to have the airplane wing rotating to make it work. So if like the engine, if I lose power, most airplanes I can coast for a while, or I've got some lift still. If you lose power, if your lift requires your wings to rotate and you lose your engine or motor, you're kind of foobar. Even helicopters, if you lose power in a helicopter, you start falling, the helicopter blade starts acting like a wind turbine, and it'll actually start spinning. And you can actually land safely. It'll be a hard landing, but it'll be a landing people will walk away from, or at the very least limp away from.
Yes.
I would jump well before the ground.
All right. But I've been told that like all helicopter pilots have to do that at least once, like before they get their helicopter license. You have to prove they can kill the helicopter. I don't know if that's true. Somebody told me that. Okay, so real airfoils. Okay, so all of that was theory. Real airfoils, we find their behavior is found from experiment. And we get these graphs called polars. And for small angles of attack, they usually look like this. So this is my angle of attack, and this is my lift coefficient, and they typically look something like this, where this stall angle usually occurs somewhere between around like 10 degrees to 15 degrees, depending on the airfoil and depending on the Reynolds number. So this would be negative 10 degrees. So remember, if I'm here, it means that my wing is pointing up by about 10 degrees. And when I'm here, it means my wing is flat. And so when I'm over here, it means my angle of attack is negative. And so this is my lift. And we also want to look at drag. And drag tends to look something like this. And so let's think about this then. When I have very low angle of attack, the wing's flowing over my hand, and there's not a big cross section. Most of the air is not seeing my wing. As I increase my angle of attack, there's more surface. The air, as it hits my wing, is seeing more surface. And at some point, like obviously, when the angle of attack becomes 90 degrees, then I should have zero lift, and at 90 degrees, my drag should be maximized. The way I drew this, if it's a symmetric airfoil, this line will cross the origin. If I did not have a symmetric airfoil, if I had an airfoil with some camber, I could, I'll give it a different color. I could get something like this, where at zero angle of attack, I still get some lift. Because my airfoil in this case might be shaped something like that. Okay, so even though my angle of attack, my chord line, I'd still get some lift there. Symmetric airfoils, they have a lift coefficient max of about 1.0. And a cambered airfoil CL max might be around 1.4, which I would like to point out is much lower than 4 pi. Which is why I think flat rotors are cool. And we know a lot more about control theory now, and I'd be interested in seeing if someone tried to create a Magnus effect driven airplane. All right. We generally think in 3 different flow regimes. So 3 flow regimes. that says regimes. In one, we have attached flow. In attached flow, we have alpha is less than somewhere between 7 degrees and 10 degrees. Somewhere in this area is when we're going to start to getting a detached flow. And at this point, my lift coefficient is proportional to my angle of attack. And again, we sometimes write this as where this is just the slope. Okay. Then we have the stall region, high lift stall. And here, this is like alpha is somewhere between, like, say, 7 degrees and 11 degrees. And it's where stall is beginning to occur. And this is where lift is maximized. And flow begins to detach. As A increases, lift decreases, and drag increases. And then we have the stall regime, or I'll say stall regime. In the stall regime, there's not that much difference between this and this. And so we typically, to get our behavior of our polars in this region, we often use flat plate theory. Basically, if at an angle of attack of 45 degrees, we assume that lift is equal to drag. At an angle of attack of 90 degrees, we think drag is a maximum. Equals 0. And basically the wind is just blowing right at it. And I should say, being in the stall regime is not necessarily always a bad thing. So one of the things we're going to learn later in this course is that wind turbines need to control their speed. And there's two predominant methodologies for getting a wind turbine to decrease its rotational speed when the wind is blowing too hard. One is the blades is called the blades pitch. Okay, so you have blades that can actually change their orientation to the hub, and the actual airfoil itself will rotate in order to change the angle of attack that the airfoil, that the turbine blade makes with the wind. In which case, if the wind's blowing too fast, they'll actually decrease their angle of attack to the relative wind in order to essentially have less lift and therefore not spin too fast. Another alternative is that we will soon learn, really in a few seconds, that the wind the blade sees is different near the hub than it is near the blade tips. The direction of the wind is different. And we're going to see why in a second. And so sometimes the blades are twisted in such a way that if the wind is blowing too hard, if my finger is the blade and this is the hub here, that this part of the blade is actually installed and not creating positive lift. And what happens is, as the blade moves faster and faster and faster, or the wind starts moving faster and faster, a larger percentage of the blade is installed. Okay? So sometimes we use stall to our advantage in wind turbine design. All right, so let me explain what I just said. So this is like kind of, all right, this has been aerospace 101, and everything I've said so far could apply equally well to an airplane and a wind turbine.
But the twist can change, right? Can the
This is also why, yeah, I'll get to that. This is also why blades are twisted. But let me draw a picture and explain this. So now we're gonna move on. When I'm gonna, I think this will be the. I'm sorry, was there a question? No, okay. All right. So this is airfoils and wind turbines. And I think this will be the last topic we talk about today. Yeah. All right. I'm gonna draw a typical airfoil for a turbine. Might look something like that. I ran out of room, so we'll say this is our airfoil. I'm gonna call this direction R. And the entire length is capital R. Now this thing's rotating. It's rotating like this at some angular velocity. I'm going to call that angular velocity capital omega, which I'm going to tend to use for the rest of the course. So it's rotating like this. Now we have wind direction. We have our wind, which if you want to call it U, because we're going to say it's the wind right at the turbine, or you want to call it U infinity. I don't mean this to be the wind way back here. I mean, this is the wind as it approaches the rotor. So it is going to have some constant length, and its direction is always this direction. Now, the blade is rotating this way. I'm going to draw, so it's got its own velocity. And so if I want to know the velocity that the blade is actually seeing, it's the vector sum of the velocity of the wind plus the velocity of its own angular velocity. But its angular velocity in this direction is the angular velocity times the radius at this point, which is, this R is not a constant. This R, the whole thing is R is a constant, but the velocity of this part of the blade is just, this is just this R1 times the angular velocity. And so the velocity that the blade is seeing at this point is this, and we'll call that U relative, or U subscript REL for relative. If I'm here, I'll call this R2. The wind speed hasn't changed, but the velocity of the blade at this point, thank you.
That was spot on.
Yeah.
Is this, so now the relative velocity here is in a different, one, it's longer, and two, it's in a different direction. So, and then here, still the title, I'm just giving myself some room. So again, my wind speed hasn't changed. My wind speed having nothing to do with the turbine, but here, now, the tip of the blade is actually moving much faster than the wind. So this omega R, or actually this is just capital R. And so now my velocity of the wind relative to the blade is in a much different direction. And it's much larger. So somebody here at Everett was asking, does this have something to do with the reason the blades are twisted? And the answer is yes. Right, you were raising your hand to say.
He was also asking, do they twist, do the blades actively twist?
Oh, do they actively twist?
Yeah.
Or is there just a twist put on them and they actively yaw, like, or, well,
okay.
no, not yaw, but
Twist.
Yeah. But the twist that's already on them, that doesn't change.
That doesn't change.
Okay.
Okay. So yeah, so the blades pitch, and I want to clarify something. I've said that this thing is rotating this way. Okay. In reality, these arrows, I drew them pointing up. They'd be really pointing this direction. Okay. So really, the relative velocity, if this is rotating this way, the relative wind velocity is going in this direction, not up. Okay, so the velocity, and so the blades are designed with a twist in them so that if you are trying to keep a maximum or a just before stall angle of attack, the angle of attack of the blade is the same or is close to, let's say, like 7 degrees, not to U infinity, but to U relative everywhere along the length of the blade. Now, I think to answer your question, in wind turbines that have a pitch blade scheme, the entire blade pitches at once. And therefore, like, the entire blade would change its angle of attack. In blades that, in rotors that use stall control, the twist is designed so the blades out here stall first, and then the stalling moves in as the wind turbine is moving faster and faster than it should.
Yeah, that makes sense. But there's no blades to this day that change that twist as you know.
Not to my knowledge.
Okay.
But I could see
blade,
like,
that
there
might
are
be
forces. There are forces, right? That are acting. They're on the blade.
Yeah.
Right. That get stronger and stronger. And I imagine you could
maybe
design like a blade that's not stiff, that's not rigid, right?
Yeah.
And the blades aren't rigid.
Yeah.
They're not perfectly rigid. But you could design one that was designed to twist in a way.
Right.
But to my knowledge, I don't know of that being done. I said this was the last thing I talked about, but I got 4 minutes, and I want to. Actually, you know what I'm gonna do? I'm gonna, rather than talk, I'm gonna show the video that I. So we talked about this the other day. So I'm gonna show this video. I don't like the title of the video. The video is one of those videos that's like, it's actually a really good educational video, but it's got a very like clickbaity title. And the title is totally bogus, but the video is a good video. So we'll end the class with this as soon as I remember how to, and I hope this will look good on the. So we were talking about this, and the book talks about this in the early days of wind turbine, in the early modern period. We designed wind turbine airfoil shapes to get the best lift coefficient and to have the best power coefficient. And what we discovered is after a few years, they didn't work very well. And the reason they didn't work very well was because they got damaged, and they found that the smallest amount of damage caused a significant decrease in lift. And sometime around the 1980s, they started changing their airfoil shapes they selected for wind turbine blades to not necessarily be the most efficient to create the most lift, but to be less, so that damage to the blades would have less effect. And I think this video is a pretty good, talks about it.
But as engineers soon discovered,
wind turbines are relatively simple. As the blades turn, they turn a generator, and that generator creates electricity.
with such basic principles, building the turbines should have been easy. But as engineers soon discovered, it took a complex mix of strength and aerodynamics.
The blades of a wind turbine may look simple, but they've been perfectly designed to harness as much power from the wind as possible.
First, to extract the maximum energy from the wind, the blades have to be at the right angle, known as pitch. Getting the pitch right is crucial, as Professor Lawrence Coates demonstrates.
Here we have a model wind turbine, the typical 3 blades. These are all flat. In a real turbine, you'd find as you go along the length, they'd twist to try and keep the angle of attack as close to optimum as.
Robert and Foreman, have you guys seen the video?
Yeah.
Yeah, and can you hear it?
Yeah.
As possible. And what I'm aiming to show is the effect that the pitch of the blades, that's that orientation, can have on the actual power you get out. These are at 45 degrees. And let me just see what the voltage is. We're getting a reasonable amount of power out there.
Now the professor reduces the pitch from 45 degrees to 22.5, so the blade should catch more wind and generate more power.
So now that it's moving, the angle of attack is actually more close to optimum, and we're now getting significantly more power.
In fact, reducing the pitch by 22 degrees doubles the power output. Optimal pitch also changes with airflow. The pitch of most wind turbines is adjusted automatically with wind speed, increasing or decreasing the angle to extract the maximum possible energy from the air. Working hard, exposed to the elements 24/7, the blades experience huge amounts of stress. Creating strong enough blades is demanding, even with high-tech materials, as turbine engineer Craig Siddons explains.
So most commonly, blades are made of glass fiber and epoxy solution. So what we see up the top here is the fiber, the glass fiber itself. It's not impregnated with epoxy. And this green color here is the impregnated fiber. So this up here is obviously not impregnated. It's quite nasty to touch, so I have to put my gloves on to touch it. It can get into the skin, into your pores, and it's altogether it's quite nasty stuff. So the reason we use glass fiber epoxy is because for the strength that it gives is for not much weight, so we can build blades that are very, very long and extract as much energy as possible from the wind.
3 decades ago, turbines began to spring up in remote, windy locations worldwide and started generating power, as energy consultant Simon Gray explains.
Behind me here today, we have the Scrobie Sounds wind farm. This is one of the early wind farms on the first interplanetary offshore. So typically, on the day like today, it's fairly windy, and we're talking about this particular array here, generating enough for about 40,000 homes. Overall, if we average it out across the year, I would say offshore wind and onshore wind is generating some 15 to 20% of the UK's energy.
As materials have become lighter and stronger, turbines have grown larger.
So if you imagine a building the size of the Gherkin in London, these are about the size of the towers. If you think about the diameter of the blades, about the same size, or slightly larger than the London Eye.
A single rotation of the largest turbine can power a house for a day. But if they're not turning, they're worthless.
Wind turbines aren't cheap. To make them pay, engineers have to keep them working constantly. Any downtime is extremely costly.
But only decades after the first wind farms were built, engineers worldwide discovered they had underestimated the power of Mother Nature.
Engineers are still finding teething problems with their original designs, and some of those problems are potentially huge.
Most concerning, these giants all over the planet were showing unexpected signs of aging, caused by particles in the wind.
You might expect that giant turbine blades could easily cope with a bit of dust and rain, but being exposed 24/7, 365 days a year takes its toll.
Believe it or not, when engineers first installed wind turbines, they thought they'd be pretty much maintenance-free. But they were wrong.
Inspections revealed that in many cases, the front of the blade, the leading edge, was suffering catastrophic damage. To keep the power flowing around the world, a solution is needed, and fast.
Any damage to the blade's leading edge means that it doesn't cut the air so smoothly. And that means the blade doesn't turn as quickly. Slower blade means less electricity generated.
So the leading edge here is very sensitive in terms of aerodynamics. Just a small defect can cause a defect in the lift that goes right the way down the blade. So it can have a huge impact on performance of the blade.
The problem comes down to the speed at which the turbines spin. It might look slow, but size is deceptive.
The blades are spinning at up to 180 miles per hour. That's almost 290 kilometers per hour.
At that speed, anything that hits the blades could cause massive damage, something these turbines off the coast of England were witnessing firsthand.
Well, you've got to remember, the middle of the southern North Sea is a fairly hostile environment. Effectively, we have sea spray, we have salt water, we have wind, all of these combine to cause major erosion on all sorts of structure, whether it be oil and gas or whether it be offshore wind. And particularly, the leading edge of the blade is particularly prone to this, given that it has that proximity to salt water and wind energy.
We might call it thin air, but the sky is full of impurities, from dust to lumps of frozen water. A simple example helps demonstrate what is happening on a large scale.
Imagine that you're a grain of sand, drop of water, possibly even a small hailstone, and you're moving along with the flow. And you're approaching the very front, or so-called leading edge of this blade. And in order to go over the top or underneath, you have to have a force applied to move you. But there's no time for that because the turbine blade is hurtling towards you at 150 miles an hour. And so you hit it. So if it's only one hailstone, it's not going to make much difference. But there's hundreds of them, and after about 2 or 3 years, these may create a larger hole. The wind will catch that and start to delaminate the turbine blade.
Sweet. All right. We got cut off.
What's his name on the marker group? Are you talking about Raphael or are you talking about Raphael? Carlos? I forgot my fucking phone. Fuck me.